welcome to the course Advanced Reaction Engineering. Today we discuss about the one parameter models, that is the tank in series models. So, already we have discussed about the segregations models in our previous class. So, today we will discuss the tank in series models or TIS models. So, in this particular models we will develop the RTD functions, residence time distribution functions ET, by considering these models, and based on that we will find the number of tanks, that is the N. So, that we will find. Okay. So, that would help us to means the whatever the reactors, real reactors we have, and from the models. So, we can predict the what would be the conversions for that particular reactors, real reactor conversions we can predict with the help of model equations or models equations that will be developed. Okay. So, this particular residence time distribution function in the tank in series, that actually describe the non-ideal natures of reactors, and we can calculate the conversions. Okay. So, this is our real reactors, this is the non-ideal reactors or the systems where we can conduct any reactors. So, in this particular reactor that we have developed. So, this is the real reactors and non-ideal systems. So, here we have developed a model. So, means in number of CSTRs we can connect in series, and then we can study the RTD. From there we can find out residence time distribution functions and exit concentration or conversions, and so how many number of tanks we have to put in series. Here 3 reactors, reactor 1, reactor 2 and reactor 3 we have taken in the models, and based on that this is model systems or ideal systems we can consider this one. This is our, for that we will develop some equations, and that would be the model equations, and with that model equations we can predict or calculate the conversion or exit concentrations. Okay. So, first we consider this is the model systems that we will discuss. So, 3 CSTRs equal volume CSTRs we have taken, and that is connected in series. Okay. So, here that reactants or tracer that would be injected here, that would be spent here, after that it would be come out from that reactors, that would be entered into the second reactors, and then it would spend some times, and then it is leaving and entering into the third reactors, and after that the exit of outlet from the third reactors we will get the final concentrations of the treasures that from entered from here. So, individual reactors we considered V, here also V. So, all reactors having the equal volumes, space time tau also, that way you can consider, that we will discuss. So, okay. So, now a tracer test if we conduct. So, from the first reactors we have to consider. So, means here all reactors we said that it is equal volume or equal size 3 CSTRs we have taken. So, tracers leaving from the third reactor. So, here this is the third reactor. So, here tracer will leave C3, here tracer will leave C2, here tracer will leave C1, here tracer concentration, that is inlet concentrations. So, now the if you do the materials that is leaving between time t and t plus delta t. So, here Et dt, Et and delta t, that is equals to this, and we can write this equals to this. So, residence time distribution functions we can write Et equals to for third reactor concentration of third reactor C3T integrate 0 to infinite, 0 to infinite concentration of the third reactor at t time into dt. So, this is the residence time distributions functions, or this way we can find out C3T dt. So, these equations are residence time distribution functions, means if you know the third reactor concentrations and different time interval, then residence time distribution functions for the third reactors we can find out. So, here first step by step we do material balance for reactors once. Okay. So, here residence time distribution for third reactors how it is, like that we know. So, now material balance we are doing for the first CSTR reactor. So, this CSTR we are considering, here the accumulations equals to inlet minus outlet. So, input equals to 0 since tracer pulse injections is there, and outlet concentrations V, small v, and C1, that is the exit concentration of that reactors from CSTR 1, and V1 is the volume of the reactors. I said V1 is the volume of the first reactor. So, and dC1 by dt is that we can write this way, and this is would be the accumulation. So, now if we rearrange and integrate, okay, then we will get C1 equals to this. If we integrate these equations and simplify these equations, so we can get C1 equals to C naught e to the power minus V t by capital V1. So, that is equals to C naught e to the power minus t by tau 1. Tau 1 equals to V1 by V. Okay. So, here this way also you can write V1 equals to V2 equals to V3 equals to V, that is the equal size CSTR, and V0 equals to V, that is the constant volumetric flow rate, and tau 1 equals to tau 2 equals to tau 3, that is the space times for individual reactors. So, tau 1 equals to V1 by V0, okay, like that tau 2 tau 3 we know. So, this way you can write. Okay. So, here if we rearrange these equations, and C naught we can write C naught equals to N naught by V1, that is the C naught. So, here C naught equals to N naught by V1, N naught equals to volumetric flow rate V naught 0 to infinite C3 D3 by V1, that we have discussed. So, here we can write the C naught equals to this way. So, now for reactor 2, material balance for CSTR reactor 2, that is the similarly if we consider the material balance for reactor 2, here this equation 3 for exit concentrations from reactors 1 that we have developed equation 3. Similarly, if we do the material balance for reactor CSTR reactor 2, and then this is the inlet minus outlet equals to accumulations for reactor 2, you can write V2 is the volume of the reactor, C2 is the concentration exit concentration from reactor 2, small v is the volumetric flow rate, C1 is the concentrations from reactor 1 that is leaving and entering into the second reactor, C2 is the second reactor concentration that is leaving. Okay, so, after rearranging and that we have developed equation 3 from equation for reactors 1 or equation 3 that we have developed from material balance of reactors 1. So, this one we can substitute here and we can rearrange this equation. So, we can get this is the first order differential equations in terms of C2 and C naught. C2 is the exit concentration of reactor 2. So, now these differential equations we have to solve with the help of integrating factors or using some boundary conditions. So, if we multiplied or using these integrating factors in these equations and taking initial value C2 equals to 0 at t equals to 0. So, then after solving these equations we can get equation 4. So, in the equation 4 C2 is the exit concentration or outlet concentrations and right hand side in terms of inlet concentration from the first reactors and space time that is given. So, here for reactor 2 we are getting this, and from the third reactor the effluent tracer concentrations would be this, okay, from the third reactors. So, third reactor is similarly means second reactors we have done the material balance, we have obtained equation 4. Similarly, for third reactors if we do the material balance and after that if we simplify the equations, so then we will get equation 5. So, for reactors 1 we are getting this, from reactor 2 we are getting this, and reactor 3 we are getting 3. So, equation 3, 4 and 5 the equations we are getting, that is the exit concentration of individual reactors in terms of time and space time. Okay. So, here tau equals to residence times distributions for entire reactors, and tau is the residence time for one reactors if n number of reactors are there. So, then tau by n that would be the individual reactors, Vi is the volume of the single reactor. So, there are 3 reactors. So, V1 plus V2 plus V3 divided by n, if you divide then that would be the Vi the volume of the single reactor. Okay. So, these equation 3, 4 and 5 so we can get. Okay. So, now substituting equation 5 in equation 1, equation 5 whatever we have got, that is the concentrations, means why we have developed equation 3 and 4 to get equation 5, that is concentration of C3, that is the from the third reactors the concentrations whatever we are getting in terms of initial concentration and space time and t. So, these equations we have developed, and here we can substitute C3. So, then we can get exit concentrations or residence time distribution functions. Okay. So, these equations we have developed equations 1 for by considering at the beginnings we have developed Et equals to C3t by this 0 to infinite Ct dt. So, now in these equations we can substitute Ct C3, equation 5 we are substituting in these equations. Okay. So, here if we substitute C3, this is C3, this is also C3. So, then Et we can get in terms of C0. So, if we simplify this equation, so we can get equation 6. Okay. So, residence time distribution functions we can get here equation 6. So, once 3 reactors, 3 CSTR reactors are in series, so then exit concentrations or outlet concentration from the third reactors we know. Once we know that, then the residence time distributions for third reactors we can find out this. So, we have taken 3 different reactors or 3 reactors having equal volume or equal size. So, then these equations we received or we have derived. So, now if n number of reactors are connected in series, so then this would be the general equations or residence time RTD equations for n reactors when connected in series. Okay. So, this is the final equation for considering nth number of reactors connected in series. Okay, nth number of or n number of reactors connected in series, these RTD equations or ET we can get for nth number of reactors. Okay. So, here general equations. Okay. So, these equations we can express in terms of dimensionless forms, that is E theta equals to T by tau, tau is the total reactor volume, V is the volumetric flow rate, total reactor volumes equals to N into Vi and space times, that is tau by N. So, E theta, that is the dimensionless forms residence time distribution functions, is this equation 8. So, equation 8 or equation 7, either one we can use. So, equation 7 is not dimensionless, here this equation is dimensionless form. So, we can use. So, now in tank in series models, pulse tracer response for different number of tanks when it is connected in series. So, how does it look like? So, equation 8, that is the dimensionless forms of RTD functions. Okay. So, here if in this particular equations, if we put n equals to 2, here x axis is the theta and y axis E theta, that way we are plotting. So, once n equals to 2, the nature of the RTD curves would be like this. When n equals to 4, the RTD curves would be like this. When n equals to 10, it would be like this. If we increase the number of tanks like that, so then it would be like this. And so, when n equals to infinite number of tanks are connected in series, so then the curves would be like this, a spike. So, means it like a PFR reactors. So, n number of CST reactors when connected in series, then it would behave like a flag flow reactor that we have discussed in at the beginnings in field lectures when we have discussed. So, nature of E curves would be like this. Okay. So, now using this residence time distribution functions, considering the tank in series model, so we can find out the number of tanks that gives equal or equivalent conversions when a real reactors we models or we have real reactors we have considered for a particular systems for the reactions. So, now to determine the number of tanks in series by calculating the dimensionless variance sigma theta square, that is the dimensionless variance. Here is the variance, how we can express that we have discussed in your previous class. Sigma square, that is the variance, equals to 0 to infinite T minus Tm square Et dt. So, this is the definitions of variance. So, if we express in terms of dimensionless, it would be like this. Okay. So, here dimensionless variance we are expressing in terms of sigma square by tau square in left hand side and right hand side. If we divided by tau, square. So, then it would be dimensionless and the right hand side would be like this. If we split up this, it would be like this, and then after simplifications equations 9 should come. So, dimensionless variance sigma theta square equals to 0 to infinite theta square e theta d theta minus 1. Substituting this e theta that we have discussed, or we have developed dimensionless forms of residence time distribution functions by considering 3 n number of reactor in series. So, this type of equations we have developed. This equation 8 we have developed. First we developed ET for third reactors, then generalized for nth number of reactors, and then we have developed dimensionless forms. This dimensionless forms equation 8 we are substituting here in these equations. Okay. So, once we substitute, so then after this part we are substituting, okay, e theta part, this part we are substituting. So, then after simplifications we can get this is equal to sigma theta square equals to 1 by n from equation 10. So, sigma theta square equals to sigma square by tau square, that is equals to 1 by n, or n equals to tau square by sigma square. So, equation 11 is very important. So, if we know tau and sigma for a particular RTD studies, so then number of tanks n easily we can find out using equation 11. Okay. So, now we want to calculate the conversions. Okay. So, for first order reactions, first we consider a first order reactions where tau I equals to V by V naught into n by tau by n's, and this is the n number of reactors connected in series. This type of equations we have developed when n number of C star connected in series. This is the equations, and these equations tau I equals to tau by n's if we substitute here. So, then after simplification the equations would be this, and if we do the binomial series expand, so up to 3. So, then up to this we are expanding this part. So, then we can get equation 13. So, this equation from where it has comes, this equation we have discussed long day back at the beginning in the few lectures when we discussed about n number of C star are in series. Then if you want to find the conversions, so then these equations we know. So, here n is very important, how many reactors would be there in the series, that n we can find out from Tang and series models. So, we have to conduct the residence time distribution, RTD study or treasure test, pulse treasure test. Pulse treasure test, what we can get, T and concentrations we can get. Once we know different time concentrations, then we can develop E curve. Once we know E curves, then tau and sigma we can find out. Once we know tau and sigma, n we can find out from the RTD study. So, from the RTD study, what are the use of RTD study? To find tau and sigma, and from there n we can find out. Once we know the n's, that n we can put it here in this particular equations. So, or this equation, this we can use, or these equations we can use. So, by that way we can calculate n from equations 11 and find the conversions by equations 12. Okay. So, from here we can find out n, and this n we can substitute here. So, this n we can find out from equation treasure test. From the treasure test we can find out tau and sigma, and from our tau and sigma we can find out n, that n we can substitute here. So, then we can calculate the conversions for that, or we can predict the conversions for that first order reactions. Let us say this equation is very useful, 1 by tau I into k to the power n. So, this n equals to tau square by sigma square, this tau we can substitute here, and tau I equals to tau by n, tau I equals to tau by n. Okay. So, here we can substitute, and this x we can predict. Okay. So, now Tang in series models is over, I think. So, one numerical problems if we discuss, then it would be very clear for you. So, similarly from the let us say Tang in series models we have a first order reactions, this type of a tracer test this not valid, but here actually this type of reactor series we have to consider, and from this reactor series we have to conduct the tracer test, and if we conduct the tracer test this time concentration value we can get if the reaction rate constant is this. So, Tang in series models, how we can find out the conversions. This is the Tang in series model. So, we have developed this, we know these equations, and after that we develop this, either both the way we can do this. So, now and this is for single CSTR conversions equations, and for ideal plug flow reactor these equations for find out the conversions. So, here Tang in series model, so conversions we can find out using this equation. So, that we already have discussed. So, now this is given from the tracer test. So, now E t and this T E t, T square E t, these are the things we can develop for individual times or individual points. Once we how to find out this? So, I discussed already in our last class that how to find out this and E t, and then how to find out this. Okay. So, T square E t we can get, T is given T square and multiplied with E t, then T square E t we can get 0 to infinite time means 0 to integrate 0 to 14 T square E t dt, that we have to do the integrations, and here we have to use Simpson's 1/3 rules. Then the value for these integrations will get means from here to there. So, total integrations the value would be 32.63 minutes square. So, this value. So, then now mean time equals to tau, that is equals to 0 to infinite T E t dt, that equals to this, and variance sigma square equals to, the definition is 0 to infinite T square E t dt minus T m square, that equals to 6.1 minutes. So, from the RTD study or tracer test we know tau equals to 5.15 minutes and sigma square equals to 6.1 minutes square. Okay. So, these are the two things we know. So, now we can find out n. We know tau square, sigma square. If we put this value, then n equals to 4.35 that we are getting. So, number of tanks equivalents to 4.3. Okay. So, now in these equations we have to substitute this n. So, if we substitute in these equations n equals to this, n equals to 4.35, K value reactions rate constant that we know small k equals to 0.25, that is given in this minute inverse 0.25 reaction rate constant for this particular reactions is given. So, that we can substitute tau and n we can substitute here. So, then after simplifications, so considering Tang in series models, the conversions that we are getting 0.677, 67.7% conversions, okay, that we can predict. So, here we have not considered or conduct the reactions, only we have conducted the tracer test by considering a number of CSTRs in series. With the help of the RTD study, we found these are the values tau and sigma square, and using this we can find out n's, that n we can substitute in these equations, general equations. So, then we can find out conversion. Similarly, for if we have a one CSTR and if we conducting the same reactions, then if you know tau and k, there also you can predict the conversions. If we have a ideal PFR, there also we can substitute and we can find out the conversions, what would be the conversions. So, these are the comparisons, or you can say that way we can consider or we can find out the conversions by considering TIS model, Tang in series models. Okay. So, now Tang in series models we have discussed. So, now this part is over. So, now something means Tang in series model is complete. So, thank you. So, today is up to this. So, next day we will discuss something else. Thank you.